Hello everyone, welcome to the second lab. In today's lab we are going to do a circuit. The circuit that we are going to execute is this one. So now this circuit is an RLC based circuit, so it has resistors as well as inductors and capacitors, and moreover it has a special current supply, which is a unit step based or a Heaviside function based supply. This is the first thing. And secondly, for this supply, I mean, it's not a unit step because it has a multiplier of 3 here, as you can see here, plus it is in the minus t time, which means that it is a flipped version. In the unit step function, the amplitude remains 0, and right at the time 0.0, like time at 0 seconds, the Heaviside function turns to 1, and it stays 1 all the time. It turns to unit step. For the minus t times, it means that the unit step function was always have some value, which is unit step multiplied by 3 amperes, and right at the time t is equal to 0, 0, this becomes 0 and remains 0. Secondly, it also has one switch, and that switch tells us that the switch was never closed. It was open all the time, but the moment this unit step function becomes 0 is the moment when this switch turns on. So the same time, when this time turns 0 and this time turns 0, this function becomes 0 while this switch closes. So these are the two different new things that we are going to learn. And for this one, this is an example again, page number 342 from your 10th edition. Example number 9.6. In the end, we are interested in looking at the inductor current. We are going to look at all those values, IC, VC, IL, IR. But just to confirm, our plot of the inductor current should be looking like this. So 2 seconds, I'm going to simulate it for like 5 seconds, for example, just to look at the plot. But the idea is that this is how it should be working, all right? So that's the idea. So let's quickly build the circuit. Heaviside function explain and switch, and I'll tell you how we use the piecewise linear functions to implement these two functions. But the main thing to remember here is this, that the moment, the time moment, let's say 1.00000, or to be precise, let's say 107 nanoseconds is the time when this switch turns on. Then 107 nanoseconds is the time when this current source becomes 0. So this is very important. The two timings has to be the same, otherwise your results will not be the same. All right, this t could be any value. It could be 2001 milliseconds, and then the 2001 milliseconds is the time when this switch turns on and when this unit step function becomes 0. This is the most important thing. So I've named my circuit already. Did I? Yes, it was here. Yeah, new file, lab to instructions. All right, this is my new circuit. I'll open it. All right, so I'll start with the instantiating. So I'll instantiate from the analog library. I'll instantiate my resistor. Okay, how many resistors do I have? Let's quickly have a look for the instructions. So I have a resistor here and a resistor here. All right, one resistor here, another one here. Later on we can fix them. Escape, instantiate. I have a capacitor, so I'll bring the capacitor. All right, here's the capacitor. Capacitor is just towards the left of the resistor, so I'll put it here somewhere. And then we have the inductor. So inductor, select inductor from here. Okay, close. Inductor is in series with the resistor. Okay, so we have 2 resistors, 1 inductor, 1 capacitor. All right, 1 2 3 4 components done. And then we have to look at the current source. As I said, that we don't have the regular current sources which can mimic this function, so we have to improvise. We have to find out a way on how to do it. For such a thing, we use something we call as piecewise linear function, which means that the information of that current source can be defined piecewise, like 0 to 1 second the value is this, and from 1 to 2 seconds this value is that, and then 2 to 3. So we can define within that piecewise linear function on how to shape our current source. So I'll instantiate within the analog library I'll go to, it's a current source, so I'll say IPWL. So here current base piecewise linear source, that's what we are looking at. And what is the direction is from rotate from bottom to the top. It is in parallel with capacitor here, as we see. I mean, here parallel just means I just want to make them in order. Okay, this is done. And now secondly, for this to mimic this switch, we have to bring in a switch. Okay, so I'll instantiate a switch. Okay, yes, that's switch. And now this switch is a voltage base, a voltage activated switch. What does that mean? That when there's no voltage here, if it's a 0 volt, we see that switch stays off. But the moment the voltage turns to from 5 to 12 volts somewhere, so I normally use 10 volts. So when a 10 volt supply is given to these two terminals here, then the switch turns on. All right, so it means that it again this switch has the function of piecewise linearity. So I mean, it stays off for some time and it turns on at some other time. So we'll go to instantiate, and for such a thing we have already seen that piecewise linear function, but we'll go to the voltage source, which is piecewise linear. All right, VPWL is the is the source. Here's my source. This is the piecewise linear source. All right. Okay. Now this source we can configure that it was off for certain time and it turns on at certain time based on a definition of the timing here. All right. This is what we're going to do. Now let's configure the. So before I start wiring the circuit, I want to configure these current sources. This is important, the current and voltage sources. So if you see that number of pairs of points for this source is 2, which means like I want 2 different timings. The time 1 is 0. All right, so 0, and at 0 time the current of the source is 3 amps, and the next time, which is, I don't know, 10 nanoseconds. All right, like second time is 10 nanoseconds, is the time when the value becomes 0 amperes. So it was 3 amperes all the time. For the time 2, which is 10 nanoseconds, we can go even picoseconds, but 10 nanoseconds or 1 nanosecond, even less than that. So 1 nanosecond is the time when this current source becomes 0. Now this 1 nano is the time when the other switch activates. So just please make sure that these two times have to correlate. They have to be the same. All right, so this is my current source. It has been configured. Now I'll go here to this voltage source. Number of pairs 2, yes. Time 1 is 0 second, and that during that time the voltage is 0. The time 2, when when our main current source becomes 0, there was 1 nanoseconds, is the moment when the voltage of this switch becomes 10 volts. So this is what we are going to do. We'll say okay, and we've done that. Now for this switch we have to set the properties for the switch. Normally what we do for the switches, when we have the short circuit in the switch and an open position, we have to look at the parameters of the switch. When the switch is open, the resistance is 1 tera ohms, which means like no current passes. It kind of mimics the real life circuit, the real life switch. When the switch is closed, 1 ohm resistance is too much. I want to say that 100 nano. Again, 1 milliohm. All right, so that's enough. All right, 1 milliohm. Did I set the value? Yeah, 1 milliohms. All right. So when the switch is closed, the resistance is in milliohms. All right. So that is done. Now please remember this configuration again. You see that I've chosen time 2 as 1 nanosecond when the current becomes 0, and I've chosen this as 1 nanosecond when the voltage turns 10, which means the switch is activated, which means the switch is closed, which is exactly what we see here. The moment this current becomes 0 is the same moment when this T is closed, which means the power supply turns to 10 volt, and 10 volt means that this switch is activated. This is very important. Okay, for the values we have 1 over 240 farads. All right, capacitor Q, hit the Q. It's 1 divided by 240. You can write the values in the form of fractions within Cadence. That's okay. I want to check and save. Okay, no problem for the these are the warnings regarding the connections not executed. Okay, for the inductor we have 10 Henry, we have 48 and 100. So we have Q as 48 ohms, and we have this one as 100 ohms, while this one is 10 Henry. 10 Henry. Okay, now we can start wiring. So we have this resistor, this inductor is connected. Excuse me. Okay, the capacitor was connected in this fashion, or connected in this fashion, and then this is connected. Even no, it's not. Okay, we can later on, we can always see in the check and save. So let me fit the window, and then this 48 ohm resistor. Okay, this switch is over here. And then this switch has to be we still have to instantiate the ground, so I'll bring the ground. Never forget the ground, please. So ground, we bring one ground over here and another ground over here. Alright, so for the last resistor it is connected wired, W for wire, and it's connected to this one, while at this point it's connected here. Alright, let me fit the window. Okay, so let me just beautify this circuit a bit. I'll just, sorry. Okay, and actually we can distribute it a little bit better, so I'll bring it a little bit closer. This happens, whatever is happening now is normal. So let me just delete this wire, D for delete. Let me delete this wire too. Let me delete the ground, and we'll copy the ground. It's something I've taught you guys how to do it. So this inductor, let us take it here. Okay. I'll bring it a little bit down. I'm sorry, I mean, this is important for me to work. I want to always try to clear up the things so they make more sense to me. Okay, undo. Alright, I think it's okay. Now for this wire, let me delete this one. I will bring the wire from W from here to here, and then for the ground, I'll hit the C, which means it'll start copying, and I'll click it, and then it has now been copied. I'll bring it here, right? Now check and save. Okay, check and save. Did it give us any warning or something? Let's see with the G. No warning, nothing. So check and save is okay. I'll just bring it also in the middle here. Okay, now our circuit is now complete. We just have to use the net labeling to label different points. So I'm going to label this one as voltage of, we have R and C here, VRC, right? This is the voltage of RC, and I'm going to label this one as voltage of RL. So label voltage of RL. And I'll also like to have a look at this piecewise linear voltage source. So I want to label it as voltage underscore switch. Okay, this thing is done. Now one more important function here is, since we will be looking at the current, for looking at the current for the in Cadence, remember that you can select these endpoints of an element to look at the current passing through the element. So you can select either top one or the bottom one. The rule here is, if you select the top one, the current in Cadence always flows into the element. What does that mean? If you are selecting the top node for this inductor, the current direction will be from top to bottom. If you select this node for the current direction will be from bottom to the top. Now, looking at our instruction circuit, we see that the inductor current that we are looking at is going from top to bottom. It means that we will be selecting the top node. As I said, in Cadence, the current direction is defined by the current always going through the element. If in case the current direction was from bottom to the top, we will be selecting this node of the inductor, the lower one, because the current flows into the element. Similarly, for this one, we'll be selecting the top node of the capacitor, as the current is moving from top to bottom, and the current has to move through the inductor. All right. So this is save. Check and save is done. The labeling is done. Now I'll quickly launch the ADEXL. Create new view. Okay. All right. Take the new test. Lab 2 instructions. Okay. Setup environment. 64-bit. Apply. Okay. We have to select this transient simulation. As I said, the output says that the values at 2 seconds will be like this. So I'll just simulate it for 3 to 4 seconds. Now there's one more important. Please guys remember that. Please remember that. I will not be repeating this. For your lab, there is a time. Let me actually quickly show you. This is important. For your, these are lab instructions. For this very lab, the output of this circuit is in this form. But if you will look at this diagram closely, you will see that all this action is happening within a couple of milliseconds. All right. So what do I mean by that? When you're looking at the plots, please do not if you simulate it for 10 seconds and if you're looking at the plot, this information might be so tiny that it won't be visible. Remember that there are good number of marks for you to zoom in the area of action, and I have categorically explained it here. verify that the plot of VC and IL looks like this and should be properly zoomed. I mean, do not try to zoom it over the 10 seconds and over the large value where these things just appear like a small disturbance. Make sure that the area of the action is properly zoomed. Okay, so this was important information, and this is what I'm going to do. I'm saying it again and again, that this is this action is for the 2 seconds, and I will be simulating my circuit for, I don't know, 4 seconds. Okay, that looks okay to me. And for the accuracy, always use the conservative, which means like more problems are solved and more data values are obtained, and you get a clean and nice plot. All right, you do this. Okay. And then we do the setup outputs. In the setup outputs, the third tab, we say, okay, setup outputs from design. Now we'll be choosing our outputs from the design. Here, come here. We want to look at the voltage of RC. We click it. We want to look at the voltage VRL. We'll click it. We'll select voltage of switch. Click it. Now looking at the currents, I want to look at the current. So for this, for the capacitor, as we saw that for the capacitor, the current is going from top to bottom into the element. So I'll go setting output. So that everything we are selecting is coming over here. The outputs we are selecting here. Where's my circuit diagram? Here. Now for this current, I'll choose the top node because the current goes into the element. Okay, now for this current, I'll choose the top element because the current goes into the element. You see these circles, they will appear when you select the second element. This shows you that you are looking at the current at the top node. And then I'll be looking at the current of this R12, and I want to look at the current of this node. Now why I want to look at this current node, I want to see that my setup of piecewise linear current source, which was it was 3 amp all the time, and at one moment this current becomes 0. To look at that current, actually I'll look at this node, right? Because I want to see the current from passing through the element. So current passing through this current source. I'll select this one. Okay, once you have selected all of it, yeah, we've pretty much selected all of this. All right, and then I'll hit the escape key. Once you're done, you hit the escape key, and then you go to your ADXL test editor, and you will see that you have the voltage, RC, RL, everything that you've selected is there. All right, setting output, you'll see all those numbers here. Say okay. Once this is okay, once this is done, we go to ADXL. I'm sorry again. ADXL, and then you run the simulation. If you don't see the simulation button here, just click these double arrows. Hit the simulation. Let's see if there are any errors. No, there are none. Go down, and you won't see any error. You see 0 errors, 0 warnings, and 5 notices. That's okay. And then quickly looking at all the plots, the best thing is, okay, I'll say replace. Okay, replace, and this is the button to plot all the quantities. So I'll hit this one, and it's going to plot all of those things. Okay, we can shorten the time from here. I'll just shorten the time to, okay, that much seconds is okay. And we were looking at just to verify our answers first. The inductor current starts at 2.2 amps, goes up to like 2.7. all right, let's see if this can be seen from there. Sorry, inductor current, this is the inductor current L0, right? So I'll just turn off all those things, everything else will be turned off. This is my inductor current. I can make it a little bit thicker. Just right click and go to the width and go to the thick. All right, now if you see that this is the current is towards the right, if you see that this is the current bringing the pointer top, it says like 2.68 amps is the top timing, 2.68, yeah, something like 2.7, and then the bottom lowest value is around 0.8 seconds, and which is minus 1.3 or something. 0.8 second minus 1.3, 0.8 seconds minus 1. Oh, this is not minus 1.8 for sure. This is telling me that it is 1. Okay, it's minus 1.2 is the maximum lower value. 1.2. Oh, okay, so this is minus 1.2, right? Let's quickly confirm. Yeah, minus 1.2, around 0.8 seconds. So this is minus 1, and it is actually minus 1.2, somewhere near the 0.8. I thought that was not clear. And then the second peak is around 0.5 amps, all right, at 1.4, 1.5 seconds, 0.5 amps. We go here and it is 1.5 amp, this peak, like here, top, around 1.5 seconds. So this confirms that our plots are okay, our timing, the way we set up everything was okay. Now I can look at everything else. So as I said, that voltage at R, so I want to look at the voltage of the current source. How did we set up the Heaviside function? So the current through the current source, this is the current through the current source. Yeah, look at this. It was, I will just zoom in here. So you see it was 3 amps all the time here, and at the moment of that 1 nanosecond the current becomes 0. Okay, this has behaved the way we wanted it to behave. And then the voltage of switch is something, it was also piecewise linear. And you see here that it was 0 all the time, but at the same moment when the other source becomes, the current source becomes 0, the voltage becomes 10, which means the switch was activated. So this is the way to look at all the plots, and you have to explain these plots. For example, looking at this, sorry, here's the where is the fit here? This is fitting the window. Now if I want to look at the, please always use different, you can use different colors, different styles. You can use this one as a dash. No, right. This line as a dash dot, all those kind of things. If you want to put more plots in one figure, do this. Now if I would like to explain this thing, I can tell you that when the inductor current is increasing, I can see that the capacitor is following the same, the exact opposite trend to the inductor, which means that the current of the inductor is being used to charge the capacitor, and once the capacitor is fully charged, capacitor starts applying the voltage to the inductor, and they both starts consuming each and everyone's current and voltages, and in the end all of this is being dissipated as a heat on the resistors. So this is kind of explanation from this plot that we can see. Now there are many things that can be done for the plots. Please, I won't be teaching you all of those things. Save images here, you can save the image. Please use the high definition image saving for that one. I've told you the procedure. Now what you can do here is this. I can go and look at this plot only. So the replace was selected. Let me select new window, which means that my voltage of, let's say, inductor here will be on a new window. So I just do this, right click and plot, and you see a new window will be opened here. Go to the virtuoso, you see there's a new window. This is the old window, the old tab, the new window, only with the inductor current. That looks more like the output plot that we've been looking at. Okay, this was in window 2, and now again we can do more things. As I said, I want you to play. I want to append my new plot, which is the capacitor current. I want to append on the same window. So I'll go here. You see that on the new window, the same window, the two plots are clear. So when you're plotting, taking images of the plots, please make sure to take the meaningful images of the plots. Do not try to squeeze everything in the same plot. Plots has to be cleared, and they should be properly zoomed. I mean, if I'm looking, as you guys saw that when I was looking at this voltage for my switch, I tried to zoom it in this area, right? Because this is the action I want to look at. This is important, and you can just hit the fit window when you want to look at all the plots. Now, these are the two ways you can look at the new windows. You can append it, you can replace, you can open a new sub window, select different colors and everything. So this is I hope it will explain all the problems that that you could face for the execution of this lab. For this lab, I'll quickly show you the first circuit. One, you have a series circuit of RLC, very simple RLC circuit, and this is important. You'll have R is equal to 5 ohm, and later on you change this to 0 and look at the output of the plot. Similarly, you have a circuit 2. This circuit 2 has a switch which is turned on all the time, and time is 0 seconds. This switch turns off. And then for the third circuit, you have this R1 as 200 ohms, and this current of the source is in the 30 unit step function of 30 amps, and there's a switch here which is off all the time, and time is equal to 0, it turns on. For these, please look at these, all the I want inductor voltages, inductor current, capacitor voltages and current, and this plot at the output. For this circuit, as it says, at just 7 seconds and plot the V out C. This is only needed. For this thing, just be thoughtful. You have to make a unit step function as an input, bring two different plots, comparing the results of all these things. I hope everything is clear, and if you guys have questions, please do ask. Thank you very much.